Let's start it over. So today we will start the first lesson of the lesson series about async and concurrent programming in C#. And this will be 8 lesson series. And the first lesson will be from an overall look at typical problems that we have in async programming and potential solutions that we could have in general and in C#. So what is a thread and what is a process and where do threads come from? Basically, one thread can run one process at a time. So sometimes we might want to do the same thing in parallel so that all the threads that we have are utilized. Optimally, we have threads running equal to the amount of cores that our processor has, times 2. Basically, you have physical core and virtual core, and each core has a thread from it. Thread is an abstraction of a core, basically, and a process is just a piece of code that needs to be run somewhere in some context. So we can distribute resources by running code concurrently. Distributing resources as in using all the threads we have to do a certain task. So it's easy to create threads, but at the same time, it's hard to manage what we have created. And so there are a whole bunch of problems that come from managing them, and there are a whole bunch of suggested solutions that we'll try to quickly look at. The first problem coming from multithreading is critical section. I mean, that's the whole thing which makes it so hard with multithreading. Critical section is basically a resource, a section where multiple threads can call it at the same time. So if you have a road with multiple cross sections like this, you have 4 sections that cross. Basically, in the crossing point, you will have cars which would crash if they don't have, let's say, lights to regulate traffic lights. So in programming, it's not as severe. When you have resource being accessed by another process, you will either get an exception or you would get an exception. Maybe wrong result, maybe an exception, something along those lines. Anyways, critical section means that there is a need to regulate it. So for critical section, like cross-section of roads, we have traffic lights. So we need to block and lock the resource until it's available for another thread. So just like we let through only one single lane to pass, we do the same regulation for our code. So we need to lock it so that critical section can run free. So we need to explicitly handle this situation so that our concurrent code can run as intended. If we don't do that, we have Deadlock. Deadlock, just like this massive hero from Marvel Comics, is really probably the biggest monster that concurrent programming has. It locks your CPU, it locks your program, and you will have a not responding kind of experience if you don't know what you're doing and if you let loose the concurrent code and let loose the blocking context. So deadlock is a state where two or more processes are simply waiting for the same resource. If no resource, if you don't let them go, you will get infinite deadlock. If you don't unlock the context, you will have infinite deadlock, and your program will simply never end, will never terminate, and you will wait forever. So deadlocks are something that we solve, that we have to deal with and solve when we are doing concurrent programming. So here's an example of a deadlock. Here was a single resource and all was good. Now we have two resources. So one resource passed, it blocked the path till it passed, and then another passed. But now we have a deadlock. Both paths are blocked, and so a resource cannot pass. Now, what can we do? We can unlock one gate, block the other one, and let the other one go when the other one is passed. So this is an example of what deadlocking is and how to solve it. Asynchronously closing the context and opening it when it's ready to let loose the resource. Asymmetrically, more like asynchronously. Race condition. When you deal with asynchronous programming, you will often notice that sometimes you have random results. Random is what you don't want in your programs, but in async programming, that's what you deal with more often than not. To deal with random, well, so that random comes from race condition. Basically, when results depend on which task did the thing first, basically, let's say if task A did the thing first, that's correct. But if task B did the thing first, or if it did it during task A was working, then it's a problem. So that's race condition. Basically, a condition which depends on which task got resources when. So we want to wait for it to end before we can work on it. We want to, again, use the same locking mechanisms and handle it. Just like we did with deadlocking, race condition is the same. We need to block some section till one thread is added. Starvation is a severe case of deadlocking. Basically, it means that you never get to use all your resources and your optimizations are non-existent, meaning that you have 4 threads running and one of them will be doing nothing because it waits for the resources are freed up. So 3 threads would be running and 1 thread would be blocked, for example. Blocked for infinity, and it's called starvation because it needs to do work, yet it cannot as it is blocked. Starvation is best illustrated by dining philosopher's problem. This is a classical concurrent programming problem. Basically, each philosopher has a fork and from their left and right, and they need to eat. If they want to eat, they need to grab forks from both their left and right. But they cannot grab a fork if it's taken. So they need to wait. So how do you make philosophers eat in union nicely, utilizing all forks? That's a problem of parallel programming, concurrent programming. So now that we define the problems, we need to solve them. And basically, the problems that we're solving involve blocking, locking, critical section. And locking can be done in using 3 structures. It's called lock, mutex, and semaphore. So locks are basically just what it says. It prevents context from being accessed by more than 1 thread. So at the same time, whatever is locked will be worked with by only 1 thread. Mutex is very similar, except that you can involve, well, it's the same, semantics are different, basically. Mutual exclusion is something that should be mentioned, which means that the whole system is involved and not just your program, if I understood correctly. But anyways, the main difference is semantics. Lock and unlock is how you use a mutex. Instead of having brackets which denote which context is locked, you have a mutex data structure which can be locked and unlocked. And the key thing here is that they let in only one thread. Lock and mutex, one thread. Semaphore is basically the same, except that it can let in more than one thread. So the only difference is that when we create a semaphore, we specify how many threads can enter a context. So essentially a semaphore which allows only one thread in is very similar to a mutex. So how do we create a semaphore? So you say how many threads can be in, how many threads can be at max in, and you can name the semaphore. And when you start a task, it will, well, utilize the semaphore at hand. With object and lock, with creating a new object, you can lock some context. And here with mutex, you can basically do the same, except instead of brackets, you have wait one, release mutex. Now, parallel, async, and concurrent programming, those all sound very similar. And probably in general, you would think they are all synonyms. But it's not quite simple as it is. They each have a meaning, and they shouldn't be mixed. So, thread is something that makes code run concurrently and in parallel. Now, what does it mean? When we create a new thread, we basically say that it will be run on a different thread than the one we have at the moment. And if we start a new core while our program is still running, that means we're running two processes now. And so they both run independently, asynchronously, and in parallel. Two processes at the same time. So parallel means at the same time. Async means they are not blocking. Parallel means at the same time. With this, I should mention thread pool. Basically, thread pool is a place where .NET stores its threads. So if tasks if threads are outside thread pool, so when we create a new thread, it's not somehow magically appearing on a thread pool. It's a new thread independent. But when we create a new task and we run it, it is being run on a thread pool. We will soon learn what the task is. So a task is running on a thread pool. It means that we are not creating new tasks. We are not creating new threads by creating new tasks. We're simply using threads that already exist to run the tasks that we need. So to run a sync code asynchronously, we can do something like this. Note that this is not the same as task. We will talk about this in the next lesson. Task.run is not a complete replacement for a wait task or something like that. Task.run basically says that the context that we're running, the synchronous context that we're running, will be put to a thread pool. it won't be parallel most likely, but it will be asynchronous because it won't block the context of main. Meaning which after task run is called but not done, our program will be over because there is no other statement left there. So what's the difference between concurrent and parallel? Concurrent programming means non-blocking, something that happens at the same time. An example could be here, you see two rows happen concurrently, two queues happen concurrently, two queues march to the same destination, and it's a really big difference compared to one queue. So two queues march to the same destination. So maybe there is a checkpoint which can accept two people simultaneously and pass them through. Maybe that's why there is a queue, two queues, not just one. Another example of concurrent would be something, let's say, cooking. Let's say you're cooking a meal, a dinner. So what do? You turn on the stove, you put water on. This is synchronous. But then you turn the stove on, put the water on, and instead of looking at the pot for half an hour, you go play video games. Then half an hour later, you go check the pot, and what happened? Well, it started boiling. Anyways, that's concurrent programming because you didn't wait and stop for the pot to boil. You went to do your bidding and came back. That's concurrent. Parallel would be that while the pot was boiling, like while we were putting stuff on the oven, at the same time you were eating an apple with another hand. At the same time, that's parallel. With the queues, you would have two checkpoints and two queues, each going for a checkpoint. So that would be an illustration of parallel. So that's the difference between concurrent and parallel. So what's the difference between sync and async? Sync context would be a context which happens one after another. You have to wait for a response, and you cannot do anything else while something happens. So an example would be sending an email. Someone sends you an email. Well, basically, when you send someone an email, you have to wait. And you have to wait for a long time usually, because someone gets the email and then they have to reply. They reply and they send the email back. You check the email box and you finally see an email. Well, you waited a long time till that happened. Async example would be that there is no blocking. You talk immediately. You talk live, and you can even talk concurrently at the same time. Basically, those two people that are talking, if they're rude, they might be shouting one over another. That would be parallel. If they're polite, they might be talking one after another. That would be concurrent, async, but not parallel. So that's in general problems, solutions, and basic definitions. So in C#, at the very start, there were threads and events, and multi-threading, async programming, more like async programming, was thread-based. You had threads, and there you could utilize threads to do your work. There was background worker, the most common way of doing something heavy, I/O, CPU bound, and events to let know when something happened, ended, and so on and so forth. But that's very old, and that's not the way it's done now. That's legacy stuff. Now we have tasks and we have async await. So task-based asynchronous pattern, other known as TAP, is how we utilize thread pool and task-based activities. We can do some task and we can await for it without blocking the context which ran the task. And that's a very simple way of doing concurrent stuff. There are a few things to note. Well, first, what's the problem with why do we need this altogether? Imagine this, loading a file, loading an images from file is a really heavy operation. If the image is high definition, it will take some time. And if we have dozens of them, it will definitely freeze your application. So the problem here is that we run the same thing on UI thread. Basically, all that runs and starts our program is called a UI thread. UI thread is already heavy as it has to keep rendering stuff. If you move to your window, it needs to be re-rendered. If you click the button, well, it needs to have a mechanism how to check for a button click. So there is an ongoing message pump with which keeps being updated based on your actions, on your clicks and presses. We want to let the loop go, keep on going the loop, but at the same time we want to do what we want, to do heavy stuff. So this is a problem because by doing heavy stuff, we will block the message loop. The message pump will stop. So we'll have freeze number 1, freeze number 2. Well, it will look like a single freeze. So for the time while images will be loaded and filtered, we will have a freeze. A better approach would be using task await and async. Basically, we're doing the same except with an async model and task model. All the heavy operations are tasks now, so we can await them. We do our tasks, we await them, and at the same time we can move the window now and it will not freeze. So what is async? Basically something that doesn't get blocked. And what is async, the keyword? It means that it allows await, enables calling await keyword. There's nothing more. Async by itself doesn't make code async. It simply enables await. So you can have async without await, but that would be dirty because you don't utilize async. So in the future, in the next lessons, we will talk about peeling queue, basically how to write link queue which runs in parallel, and we will also talk about TPL, other known as Task Parallel Library, basically how to run code in parallel, not just asynchronously but in parallel, how to enforce using threads to do our bidding, because with tasks we don't know if it runs on 1 or 2 or 3 threads. It's quite hard because it's all up to the thread pool to decide. But with TPL, we can enforce that. So the next lesson will be about in-depth task, how to work with it, how to run it, how to block it, how to cancel it, and so on. The lesson after will be about peeling queue. The lesson after that will be about TPL. And after that, we will talk about more practical applications, building something of our own, and demonstrating it all in complete practice. So that's it for this lesson, and thank you for the time watching it. See you next time.